Okay, so I've learned quite a bit in the last day or two, and I'm going to share today at a kind of a high level some of the concepts and some of the lessons that I've picked up along the way. And while I'm at it, if you want to get more into detail about some of the code, some of the decisions that I made, then you might go back and watch the Librosa and Spectrogram video that I posted, I think, on Friday. Well, when you're watching this, it doesn't really, time and dates mean nothing to you. But so let's just jump right into it. So, backing up quite a bit, if you start off with kind of the hello world of machine learning, you're often going to be looking at the mints data set, or you're going to be looking at handwritten digits. And it's really easy to reproduce those examples, but you don't learn a whole lot just by running a little block of code and reproducing these classic examples. I mean, you do learn some, but for me, I wanted to dive into something that was a little harder. And without realizing it, I picked a pretty challenging problem, trying to identify ambient soundscapes and what's the predominant sound within an audio clip that has a lot of noise. It has some challenges, but we'll get into that in a minute. But first, let's talk about where we got. And I'm just going to jump ahead to this last Urban Sound 6 notebook with CNN. Might be a good place to start. Let's talk about CNN, convolutional neural nets. My initial tests, my initial concept was to take a spectrogram, kind of downsample it or reduce the size of it to where I can still have the essential features showing. I can easily identify the image with my eye, but without so much resolution. And the reason why was I was trying to make it work with a neural network, just a classic neural network, fully connected layers. And I basically wanted it to work just like the the examples that I had found for handwritten digits, for identifying handwritten digits. And basically, that was the same little blurb of code I was using. It's getting to know the Keras API, getting to know TensorFlow, and in doing so, I was getting pretty terrible results: 50%, 56%, 62%. And so I backed up and realized, as I continued to research or just to read up on this, that for spectrograms, there's a better way to do it, and that's convolutional neural nets. Now, I'm not going to get into the conversation about how that works exactly, because I'll just end up rambling forever. And also, I could describe it, but I'll be bumping around a bit because it's also just something I picked up yesterday, right? So I just was reading up on it yesterday, immediately applied it, and started getting much better results, but at a cost. So very quickly, let's run through the code. As before, I start off by including my essential libraries. I pull out my class names from the labels that were stored on disk. I had refactored my code somewhat to be in smaller functions, making it easier for me to reuse it. The one new concept I picked up last week was how was I going to deal with short sounds? Most of the sounds in the urban sound data set are 4 seconds in length, like, I don't know, maybe 60 or 70% of them. And then there are a number of shorter sounds. And it's like, that wasn't going to work for me because to be able to run them through the algorithms, I needed them to all be the exact same length, the same number of data bits, and in the arrays, the same shape essentially. And so I ended up using a time stretch algorithm from Librosa, which is super cool. And if you ever do audio work, then you know what time stretch is. It basically takes a sound and, without altering its pitch, stretches it out to a certain length. It introduces some artifacts, but I thought essentially it's going to give you the same signature, the same frequency bands. It's just over time, and then it'll line up. So it seemed to work out pretty well. I also had added a function to drop frequency bands. This is when I was trying to shrink my data size. But in this particular sample, I took it back out. And that's because I was having pretty abysmal results. As you see with my last two attempts, once I had my shape downsampled the way that I liked it, using the regular kind of neural network configuration and RMS prop optimizer and sparse categorical cross entropy loss, I was getting it would train fairly quickly. However, my accuracy was 61%. That was pretty lousy. Once I switched over to a convolutional neural net, I said, I only bumped it up to 65%, and that was not what I expected. And I thought I probably thrown out, and that convolutional neural nets are typically used for processing imaging data. Okay, I wasn't going to get into it. I'll get into it a little bit. If you can kind of imagine a picture broken down into blocks, and then a little subsection of those blocks broken down a little bit more and generalized. That's kind of how it works. So it's meant to work with a lot of complex data or in other words, a feature set with a lot of with it's a large feature set. Okay, so you're not looking at like 5 or 10 or 15 features as you might in a simpler neural network. You may be looking at like 1,000 or how the width. If you imagine a photograph, how many pixels wide is it? That's going to be the number of features that are included. So I'm like, well, maybe I should just throw the data that I had thrown out back in, and that's why we see over here in my next two samples, I upped it to 1025. Now I decided on this last time around, I wasn't even going to bother with running this test because really, without the CNN, I know that the results are going to be poor. And also, I had tried something like this way early on and got abysmal results. Again, because I have so many features, it was not going to generalize well using a simple neural net. So with the convolutional neural net, I was able to get 88%, which still, by machine learning standards, is poor, but was much better than I'd been getting before. But what was the cost? The cost was the training time. Training time took forever. So here in my wave to STFT function, you'll notice I had previously dropped the frequency bands. I just commented that out. I calculated my data and I saved it. Again, I've been saving off my massaged data sets as NumPy binaries so that I could just load them back up without having to step through this process again. Because like this takes maybe approximately an hour to run. It reminds me of the old C++ days. It's like make a change. Oh, somebody checked in a header file that's included by everyone. So you check out the code and then you go to get to work and you have to wait for an hour because you're waiting for compile time. Hated that kind of world. It's one of the reasons I love working in Python is because I'm not typically waiting, right? I can just do, and the work is ready to go, and I just jump in and I start becoming productive. But with this, you can't get into too much of a hurry because some operations take a while. And I'll get into that a little bit more in just a second. So I load up the results. I split my training and test data from the previous videos. I had been doing this more manually, the splitting, but I found that sklearn has this nice train test split function, so I started using that. And another thing I started doing was pulling out not only just splitting my data into training and test sets, but also into validation sets. And why would I do that? I was like, what is this third set of data that now I'm keeping track of? I printed out the shape of each. So you see, I've got 1025 by 173 is my central shape. I've got 3,799 in the training data. I've got 1140 for validation, and then 489 for test at the very end, after everything is done. So validation is passed, and I have to do the reshaping as typical. There's one more dimension because this algorithm works. Expects another dimension. If you're working instead of a spectrogram, if you're working with an image file, of course, for each individual pixel, you've got 3 digits that represent the color at that pixel. And so if it's RGB, it'd be red, green, blue. And so in all of the samples that you will find that, when I say samples, I'm just talking about like example code snippets online, or whenever you're doing your research and you're reading up, you'll usually see a 3 here at the end, and that's why. But in this case, I need to reshape so that it will fit for the 2D convolutional, this right here, convolutional 2D layer. And so you add this, you just have to basically specify, look, we're only looking at 1 digit there, but it'll match the shape. Okay, so back to validation data. With validation data, you pass that in as it's training, and a few more calculations are done to see how, as it's working through and it's training and it's improving its accuracy and the loss is going down, it will also make some on-the-fly comparisons to this validation data, which is kind of like test data. It's basically we're not training on it, but we're using it for comparison to come up with this additional number. Okay, now we're going to get into the model itself. Now this is Again, kind of boilerplate. It's like I didn't have to make a lot of decisions here. I just looked at 3 or 4. I read a chapter in a book about convolutional neural nets. I found 2 or 3 samples online. I thought this was like a pretty common pattern, so I basically followed it as far as the number of layers that I included. So this is only like I've got a 32, 64, 64, 128. So I got four convolution layers, and in between each there's a max pooling. You have to flatten it out at the end, flatten it out to like a flat array. Then you end up back to the 2 dense layers, dense 5, 12, and 10 softmax, just like I used in my original sample. So my original model was just these two layers only, none of the rest of these layers. Okay, that gives you the summary out. This is becoming very usual now, and I'm getting used to seeing this. When it's funny when you first start digging into this stuff, everything seems foreign. Every time you flip anywhere, you're like, it's just so weird. What is all of this stuff? And if you're a programmer, if you just have an analytical mind, you want to dig into every little detail, and you can go down so many rabbit holes that you never end up getting anywhere, which is why I found it personally challenging to jump into here. If I hadn't given myself this goal, it's like I'm going to take some of my time, I'm going to create a little video series about me learning, I might not have had the patience to keep going, right? Because now I have like a deadline for myself. I'm like, well, I expect to have the next video in a series. I'm just going to jump in. And then all of a sudden, all of these things that are fairly fuzzy all start to come together. You don't have to, like, so for example, now the models make sense to me. The layers make sense to me. This is just a little summary of it there. Compile, I'm using the same optimizer as before. Metrics accuracy, I'm still using sparse categorical cross entropy, which is what I used previously on the simpler neural net. I batch it out, I make sure that I can get some results back, and then I go ahead and fit the model. And here's where things get hairy. They're not hairy, they're time consuming. Okay, so for each epoch, I'm only doing 16 epochs, but because my data set is large, and it's, I mean, I would say it's that large, but it's got 10, 25 features in it. It takes a while to work through this. So my little laptop here is it was churning. I went to bed last night. I don't actually know how long it took for it to get through there, but the training was maybe 2 hours. Well, if you can imagine, when I had the smaller data sets, the downsample data sets, I could make some tweaks, run it again. I wait 5 minutes. I make some additional changes. But with this kind of a train time, this is a problem, right? Because I can't just make a little tweak, let it run for 2 hours, come back and make another little tweak. So yeah, that's a big problem, right? So I immediately start to think to myself, okay, well, I have this old workstation. Well, the old workstation isn't great. It does have a video card in it that's relatively new. I actually have to get it running again. My workstation is that workstation. I haven't turned it on for probably a year, but about a year ago I was using it. And the reason I went ahead and bought another GPU is because at the time I was messing around with Blender and rendering video, and I was getting pretty decent speeds. All of that to say, one solution is to go off, buy a new motherboard, get a lot of RAM, get a lot of CPUs, buy a bunch of video cards, and before you know it, I'm $9,000 into it, trying to build my own little machine learning workstation at home. So that's not what I want to do right now, because that's not in the budget. So we're not going to go that route. And so then I start to think, well, okay, surely there's a nice, easy way to distribute my training, right? So I started looking into AWS. I wonder if there was something like the Lambda service where it's nice, it's easy to set up and easy to use, and because already batching is a very common thing. You can batch the training process, right? Where like in each batch will go off and independently work on a different GPU or CPU, and then the results can be aggregated together. So look on Amazon, they have some white papers and they have some guidelines, but it certainly wasn't something that I could in just an hour set up. It was, even though Amazon does have, I could pull it up, but I'm not going to. They do have some scripts out there for setting up your own cluster. Also, I'm not sure what kind of cost I'd be getting into with that. So I was like, okay, that's not necessarily the solution I want. I haven't tried it yet, but what I think I'm going to do is move my notebook back onto collab.google.com, which is their online notebook platform where you can build your notebooks out there in their cloud. I'm assuming they already have the infrastructure out there that will run much, much more efficiently than in the background. So what's the pros and cons to using Google's uh, collab feature, their online Jupyter notebook kind of feature? They have some really cool features, right? Well, first of all, it's running on someone else's hardware. You don't have to install anything. You don't have to install, TensorFlow or Python. You just can do everything in the browser if that's the way you like working. Maybe not my preferred way, but it would work. Okay, that's fine. The other downside, and then of course they have some nice sharing. You can share as a GitHub gist or gist. I'm not sure how you say that. It's one of those things I always read and I never say out loud. There's other kind of exporting, easy exporting to share your samples with other people or your notebooks with other people. But ultimately, I think the thing that I kind of hesitate on is like, you're basically doing your work in front of Google to benefit their research, right? Which is not like I have anything to really add, or maybe I will, something that will add to Google that they will want to see. But it's just like I feel like I'm becoming. It's kind of like working on Facebook. You're becoming part of the data set for that entity, and I'm like, do I want to do that? And I'm like, okay, I'll probably do that because if it gives me the efficiencies that I want, I'll go ahead and work on my private projects, but basically in front of Google or whoever is a Google employee who wants to look at what I'm doing and evaluate it. That's fine. I pretty much trust Google. I consider them white hat guys, even though I could go ahead and get into a story about the one time that the big giant corporation caused a problem for a project that I was a part of, but I won't go there. Okay. I digress. This is why I should probably keep a script on the side so I don't actually just go off, but it's okay. This morning, I just want to kind of talk at a high level. So let's get back to the code, shall we? Okay, great. So we go ahead and we do our training. It takes a long time, but I end up with fairly good results, right? I get like a 80.879 accuracy. And I'm like, okay, that's cool. Well, I know I didn't want to have to reproduce this training right now. And until I move it off to Collab or some other place where I can train more quickly, I probably won't continue to tweak this one. And even though 87% is kind of abysmal by machine learning standards, there are it's maybe not as bad as you might think for this particular case that I'm working with. So let's jump over to that. Found this article. What's wrong? Come on back up here to the top. What's wrong with CNNs and spectrograms for audio processing? This was a very good article, Daniel Rothman. I'm glad you wrote it. And it makes a lot of sense too. Basically, the issue is a spectrogram is an image, right? It's a visual representation of audio, but it's also different. Like if you take a snapshot of a building like we have over here, it's just like if you're thinking of a video, that would be like the image over time. And here, a snapshot like this is like, well, this is one slice. This is one representation of this moment in time, and this is what it looks like, and it's fixed, right? There's no two ways to interpret this. I mean, there are, but I'm saying in general, if, as a human being, we look at this, we can go, that's like a nice little town along a river somewhere in Europe, I imagine. We're not going to also think, or it could be an optical illusion. I mean, there are things that look the same, but for the most part, that's just actually what it is. There's no way I'm going to look at that and go, oh, it's just a mountain. That's a mountainscape that's been cleverly painted to look like a bunch of buildings. Okay, but whenever we're working with audio files, and we generate a spectrogram, we're not looking at a moment in time. The spectrogram is the entire video. If you imagine that, a spectrogram is like the video, and each little vertical band is the frequency spectrum. 1025 of these guys, right? At least in my case. It's basically from the lowest to the highest frequencies. It's taken a little slice of time. Let's say, I don't know what it is. We're using STFT, which is, I believe, short time Fourier transform. So we're grabbing a slice. Let's say it's a half a second. It's not that, but let's say it's a fraction of a second. We're saying for this fraction of a second, we're able to generate the Fourier transform, and we're able to say that this is the power. This is how much power there is all along the frequency band from top to bottom. And that one little vertical slice, that's the picture. Okay. The representation left to right, that's like a video. This is like over time. Here's the sound, and how the frequency changed over time. And so it's not exactly analogous. So those like myself who are trying to use a technique that was developed for learning from photographs and applying it to audio will find it's a bit imperfect because it's not really analogous. The other thing is, I talked about the building. It's like, is it a building? Is it a mountainscape? There's no two ways about it. But there's lots of ways that audio frequencies can be very, very similar, right? So when you're thinking about like the sounds of just got in any cityscape, you get very close to an air conditioning unit, but you're in a city, you're picking up all the noise of the city, and you hear this kind of sound. Okay. And then if you go out and you're sitting next to some other part of the city, you have all the city sound noise, and then there's someone moving. It's like a big dump truck or something, and it sounds like it's not that different. Okay. There's the audio signature may be similar. The frequencies are all the same. It could be happening, but it's very difficult to distinguish between those two. Okay. Um, what else is he going to? This is basically what I was just talking about. The axis of spectrograms do not carry the same meaning. The spectral properties of sounds are non-local. Sound is inherently serial. Anyway, in so many words, and in probably more concisely than I would say it, this article touches on why it's difficult to get like a 96% accuracy score, and to generalize this model in such a way that I'll be able to walk out and just anywhere I go and grab. But actually, with this 87%, I'm still kind of impressed with it. And so let's go jump down to the bottom. It's like, so we have, again, being this urban sound data set comes with the labeled data, which they call the train data, which I've broken out into test, train, and validation. And then there's an unlabeled set. And again, the unlabeled set is so that others can test against that and upload their scores to Kaggle, which is something that I'm not really approaching this whole process because I'm interested in Kaggle contests. I'm just learning, so I'm not going to worry about that so much. I will briefly touch on the fact that I won't get into it too much, but for overfitting, you can kind of compare your validation loss to your training loss to see where it starts to generalize. I'm not going to get into that right now. Also, mainly because there's still some things I need to learn about that before I try to talk about it. So I'm going to load up my unlabeled test files after running through the same processing I did before I did the learning. And again, I don't have labels, so the only way I can really validate these is manually. I run them through the process. I run the predictions on them, and I can load them up and listen to them and see if they seem to make sense with the label. And that's what I've done here. That's how I can ignore that. I did my predictions, and here's what I've got. My model predicts for these 10 files. The first 10 files, that could have been any of them in the set. Shows me what the model believes that this is. So 3957, it thinks it's an air conditioner. Let's listen to it. Go ahead and jump in here, slap in a 0. 3957, that's correct. Come down here and play it. A lot of noise in that one. Could it be an air conditioner? It's funny because I think it's both an air conditioner, but there's something way in the background that sounds like a jackhammer to me. And actually, if you go and look at the distribution for that particular guy, you can see whatever is at position. Let's see, was that 10 and 6 are both pretty close. Here at 6 is, oh, okay. Then we got 9 over here. So the model was like, yeah, I'm hearing a lot of those sounds in there, and I'm not even going to take the time to look them up, but I'm guessing you're going to find a mix of jackhammer in here. One of these is probably jackhammer. I don't know about children playing. I can't remember what the other one is. But let's move on to the next one. So the model predicts that 2146 is children playing. Let's pull it up. 2146. Yeah, that's good. Let's try the next one. 3922. It says 3922 is an air conditioner. I'll buy that. Yeah, 4090 sounds like drilling to me. That's good. I mean, drilling and jackhammer, I can see how those two, they both have like a signature, an audio signature that's pretty distinct, but also it could be kind of, especially in a really noisy room, I would think they're pretty similar. But it got drilling right. 3245 predicts to be children playing. That's good. Let's see what we have here. 3457. Jackhammer. Yep, that's good. The next one should also be a jackhammer according to the model. Yep, 2716. Three jackhammers in a row. Different, but all predicted correctly. Now this one's interesting. 4727. It says it's street music, and if you listen closely, I hear a bunch of talking. I hear noise on the street, and I do hear music in the background. I hear a pitch going up and down, but it's kind of in the background. Listen. It sounds to me like there's like 3 blocks away there's a parade. So I don't know. Is it right? Is it wrong? 4777. That's the last one I pulled up here to look at. And again, correctly getting jackhammer. So to me, to my ear, I mean, I'm not able, even though this only had an accuracy of 88%, the model's only predicting 88% accuracy. As a human being, I'm not certain about the additional 12%. So and what I did find here generally is, again, unlabeled data and just manually checking it. The model's checking out. It's doing a pretty good job. It's doing I think a great job, almost as good as I can do, is making sense out of these street noises. So for me, this experiment has been successful. I've learned about the benefits of convolutional neural networks and why it works better with the spectrogram than just a simple neural network. I've learned some of the downsides with working with spectrograms, and I don't know. I feel pretty good about it, and so now my interest is kind of going in another direction. So this may be as far as I take this particular urban sound video series. I hope you've learned a lot. I've learned a lot through the process. I got kicked off on this about 1 week ago, and then I spent a little time on it each day in between other client work and other kind of obligations. And I think I've made some progress here. So I hope that if you followed along, you have too. And good luck. And I'll be back with more videos as I have time to do them, because if you can stand to listen to me say, I'll listen to this back later on and go, gosh, do I want to spend an hour editing out all of the times I go, such as video life, right? Okay. Well, anyway, nonetheless, hope it was helpful to you. It's been fun for me, and peace out.